My name is Shaswat, and today we are going to talk about different ways to scale Pandas and Python for distributed systems. So first, just a brief introduction about myself. My name is Shaswat, as I said, and I'm a staff ML engineer at Lyft. I'm the tech lead for the product offerings group, and this is the group which manages Lyft variants such as shared rides, wait and save, and priority pickup. So everyone here has probably used Pandas, and it is a very loved interface, but it has its limitations. The first one is that it is single core by default. And the second one, it's a very common refrain that you need 40 gigabytes of RAM if you're using 8 gigabytes of data. So Pandas is, in short, not memory efficient. It is also limited to a single machine, and if we need to scale, then we need to utilize other frameworks. So the question is, how do we actually scale? What we want to do is to start from existing computing logic, which is local and small scale, and then utilize the power of distributed systems. Now, the way we do this is by the introduction of a semantic layer. Now, these semantic layers can be mainly categorized into two types. The first one is Pandas-like, and this is referring to the interface with which the developer interacts with the semantic layer. And the second one is SQL-like. Before we go any further, I'll also briefly touch upon distributed computing frameworks. These include things like Spark, Dash, and Ray. Broadly speaking, they support horizontal scaling versus vertical scaling, and they have added functionality like lazy evaluation. However, they require learning new syntax and concepts such as partitioning and persisting, and the developer experience is not as nice compared to pure Python or Pandas. So how do we reduce the barrier to entry for this? As we mentioned earlier, the semantic layer is a way to do that. And there are three semantic layers mentioned here. One of them is Modin, and there's Koalas, and there's Fugue, which we'll talk about more a bit later in the deck. So what are the limitations if we use Pandas-like semantics for scaling distributed systems? Before we go any further, I'd like to briefly discuss the data frame that we're using for the tests and profiling we do in this section. Here, this data frame has 4 columns, A, B, C, and D. Columns A and B are strings. Column C is a random number which goes from 0 to 1, and column D is an integer. And we'll use this data frame to test the performance profile of Pandas, Koalas, Dask, and Modin. So the first assumption that Pandas makes is that the data is physically together. For this particular benchmark, we'll use a data frame with 1 million rows. And here we have several cases. The first 2 cases are trying to access the head and tail of the data frame. The latter 3 cases, they use iloc to directly access certain row numbers in the data frame. So before we actually read the table, I would like to discuss how we are doing the performance profiling. So here, everything is relative with respect to the framework itself. That is, the intention here is to compare the relative performance of different cases from the same framework. So for instance, if you look at 0.64, which is the number for Pandas and case 3, what this means is that it takes 64% of the time for Pandas to do case 3 compared to case 1. And that is how it goes for all the rows in this table. As we can see here, Pandas has a significant performance advantage if we use iloc. However, we do not necessarily see the same in Modin. And for Spark, there is a distinct disadvantage if we use iloc. For Dask, the use of iloc is not even allowed, and that is actually a good thing because it makes the user very deliberate about not using things which may cause a performance penalty. Another assumption that Pandas makes is that the data order is preserved. However, that is not necessarily the case with all distributed systems. Here we are using the same data frame as the earlier case. What we are doing here is we're sorting the data frame by a particular column and then computing the difference and the standard deviation of that difference. Once we do that, we write the data frame back to disk and we read that data frame again and we try to compare whether the data frame X in this case, is equal to y. Now, as we can see here, that this happens to be true in all frameworks except Spark. And the reason that it is not true for Spark is that the row order is not necessarily preserved on reads and writes. Pandas also assumes that data shuffling is cheap. And data shuffling is something which is relatively challenging for distributed systems. For this benchmark, we have a data frame with 100,000 rows. And what we want to know is what row has the highest value of C for each unique value of D. There are two methods of doing this. The first method simply sorts the data frames by the columns C and D, drops duplicates. It is an elegant way of expressing this logic. However, it involves a lot of shuffling. The second method here does a group by and finds the index of this highest row, and then it merges the result back into the original data frame. In terms of performance, we can see that Pandas is actually worse using method 2 versus method 1. However, all distributed systems show a distinct advantage using method 2 compared to method 1. And that is because there is less shuffling involved in method 2. Pandas also assumes that indices are beneficial. Indices can be used to speed up Pandas operations, but it's not always true when we take this to distributed systems. In this particular case, we set the column A as an index and persist it if necessary. And then we try to find the subset of column A with the value read and the sum of column C in those particular rows. There are two different methods of doing this. The first method simply accesses the column values directly and computes the sum there. The second method indexes first and then uses that index to perform the same operation. Here we can see that Pandas is faster with the second case. However, that is not the case for Modin, which is significantly slower. Pandas also assumes eager evaluation. However, lazy evaluation can be used to sometimes both reduce computing requirements and reduce the time taken for computation. It is not, however, entirely without risks, as we'll see later. In this particular benchmark, we created a Parquet file with 40 columns and 2 million rows with random numbers. What we want to do here is to find the minimum value of columns 0 and 1 in this particular data frame. There are two ways of doing this. The first method reads the data frame and then finds the min for all columns, and then we access columns C0 and C1 min. In the second method, we specify that we only need the min for columns C0 and C1. What we see here is that Pandas is not significantly faster, and neither is Modin for case 2 versus case 1. However, Spark and Dask, they're able to recognize that we don't actually need to read the other 38 columns, and we can just read columns C0 and C1. And this greatly speeds up computation. This is only possible because Parquet is a columnar data format. However, with this, you can see the advantages of lazy evaluation. However, lazy evaluation can also create slowdowns. This particular benchmark is similar to the last one. However, instead of just computing the min, in case 2, we are also computing the max and the mean. What we see here is that instead of being faster, Spark and Dask are actually significantly slower in the second case. And that is because it is likely the case that there is duplicate compute and the compute engine is reading columns C0 and C1 3 times for the 3 different usages. It is possible to prevent this computation by specifying to the system that we can cache the result in sub, and then that way we do not need to read the data again and thus minimize the expensive I/O operation. However, that requires the introduction of new syntax and new computing logic as well. So let's just go over expectation versus reality for Pandas-like semantics for distributed systems. The general expectation is that the learning curve is flat if you use a Pandas-like system for developers, and the migration effort is low. That is not necessarily the case. As we saw earlier, if we want the computing logic to be optimal, then there is no flat learning curve. You actually need to learn new concepts. And it also requires introducing sometimes syntax which is specific to the system that we're using. That also introduces vendor lock-in. Now, This is true not just in the programming interface, but also in terms of execution behavior, as we saw from the benchmarks. So broadly, it's not necessarily the case that using a Pandas-like interface is low effort or low migration. The next section talks about limitations of using SQL-like semantics for the same use case. In this case, we use a different data frame for benchmarking. This data frame contains values from different time series. Here, the name column specifies which time series it is. We use the column IDX as a timestamp just for the sake of simplicity. And this data frame has values from several time series in this. What we want to do here is to find the rolling z-score for each time series and thus do anomaly detection. Here's a Spark-based solution based on traditional SQL syntax for this. Now, as you can see here, there is a lot of boilerplate code. The first thing you note here is that we're using CTEs, so that requires using the usage of with and as statements. In addition here, you also see the usage of partition, order by, and there's like repeated logic for this. There's also vendor-specific syntax. Specifically, if we look at the read operation here, this format is specific to Spark. And that would mean that we need to migrate this if we want to move to a different system. We also see that Spark in general, or rather SQL, lacks syntax for grouped map, persist, and distributed computing specific logic. Another limitation with Spark is that all this is a single task. And this is all expensive and difficult to develop, namely because of two reasons. One is that it's very hard to debug logic such as this. And then recomputation is also possible if you do not write optimal SQL statements. Here is the same logic rewritten using Fugue SQL. Now, note a few key differences here. Here, the load is expressed in a specific format here, and it's very deliberate. This also means that if we switch to a new system, then we need not change how this works. Another thing that you notice here is the ability to assign the result of a particular subquery to a specific variable. Even though it's possible to assign the result of subqueries to specific variables, it's not always necessary. As you can see in the first case, it's still anonymous, and you can still access the values later in the logic. Another thing which is possible to do in Fugue SQL, though not demonstrated here, is to return more than one output. This is not all Fugue can do. You can also leverage Python with Fugue. Here, we are expressing the logic for computing the z-score in the form of a Python function. If you look at this Python function, what this does is it changes both the x and y dimensions of the data. And this is not something which can be expressed as a UDF, and it's not a standard SQL operation where you need to have a return value for each row of the data. Now, using this written Python function, we can express the same logic in a much more concise fashion, as you can see below. Let's look at the performance profiles of all these various options. As you can see here, the first two options are roughly speaking similar. However, you see a significant performance advantage in the second option, and that is largely due to the introduction of the persist keyword. And you see even further advantage when we move to Fugue SQL with the Python function. This also helps in reducing the code size by a lot. Another thing which I forgot to mention is that this is a Python function. What that means is it's fairly easy for us to write unit tests, and that means that it's less likely to have bugs, and it reduces the maintenance overhead if we try to migrate this logic or to modify this in some way later down the line. So as you can see here, Fugue has the possibility of reducing both the code size and greatly reducing the execution time as well. Let's take a step back and look at local versus distributed computing. It is like moving from integers to real numbers. It is not possible to do so without learning new concepts. That includes things like persisting and partitioning. And for us to take full advantage of it, we need to change our way of thinking. As a semantic layer, the mission of Fugue includes keeping operations simple but very deliberate. That is, there is no magic in it. And then it is also set up in a way which lets us adhere to best practices in terms of structuring code and logic. Next, we'll just briefly talk about Fugue transforms. As we mentioned earlier, Fugue is an abstraction layer for distributed computing. The benefits here are increased iteration speed for developers, reduced maintenance overhead, and better adherence to best practices. So here are two operations. The intention or the logic in these operations is the same. The first case is written purely in Python using Pandas. The second one uses Spark. And as you can see in the second case, we have to introduce Spark-specific syntax. And it requires a lot of effort on the developer to migrate the logic in the first case to the second case. However, if we were to do the same thing with Fugue, the same logic here is expressed as a simple Python function, which has, again, the same advantages where you can do unit tests. And you express this as a very simple transform function. Now, this is not all you can do. All you need to do to move this from local compute, which is what this is based on, to Spark, is to introduce a Spark session and pass it in as the engine argument. And this is not all you can do in terms of Python functions either. Here, the same function can be expressed in many different ways. You can operate in pure Python and not use pandas at all. And you can use the yield statement, as you can see here. You can also just return like a data frame. And all these will be equivalent in terms of the output. So just to bring it all together, I'd like to mention a case study where we scaled a model in production to distributed systems. Here, we introduced a model to replace a rule-based system. This model was trained on roughly 20 million records of data. The model pipeline, very briefly, was implemented as a single task. Here, you had 3 steps. The first step was to query the data with SQL, which was the most time-consuming part at, roughly speaking, 2.5 hours. The second step was to do feature engineering, which was accomplished using pandas. This took around 30 minutes. And then finally, the training itself took 60 minutes. What we saw after the introduction of this new model was that we were able to perform better in terms of both outcomes and business metrics. So the next step here was to train on more data. However, this is where we ran into issues with scaling. And even the biggest single AWS instance could not handle more than 60 million rows of data. And this is where we used Fugue. The first thing we did here was to change the query from just using SQL to using Fugue SQL with PySpark. With this, we were able to cut down the time taken for the first step from 140 minutes to 20 minutes. And this greatly reduced the time taken for feature iteration, because it's not just feature engineering. You sometimes need to modify your query itself to get new features. And then the second milestone here was to use Fugue transforms for feature engineering. Now, this let us do certain operations which is just simply not possible on a single machine, and also let us scale to more data. This is where we are right now, but this is not all you can do with Fugue. In theory, it is possible for us to do a milestone 3, which would then use distributed computing for hyperparameter tuning for the training step. And another thing that you note here is that this migration was not a one-off effort. Here, you could do this in steps. Here, M1 was like a separate milestone, and then M2 was accomplished at a later date. So in short, Fugue is quite flexible, and it can greatly reduce the iteration speed, as we saw from this particular use case, and also increase test coverage and reduce maintenance overhead. So with this, we are at the end of the talk, and here is our page for our links and contact details, and we can do questions right now.
So we have one question from JD. What are the limitations of Fugue? What does it do poorly?
Sorry, Kevin, there was echo. What did you say?
Sorry. There's one question from JD. What are the limitations of Fugue, and what does it do poorly?
So, I mean, nothing is perfect. Right. So as you saw here, Fugue, in terms of its principles, it's not magical. So there is migration effort. And then even though the engine itself is replaceable, that doesn't necessarily mean that we have support for all engines, and we need to kind of build as we go. And at this point, I would like to clarify that I'm not necessarily a core developer of Fugue. I am more of a user. And this is a very good question. So we might want to actually put this in the Fugue Slack, which is mentioned here.
We have other questions coming in. Question from Paul. I know there has been some efforts from Spark to create a more Pandas-like API. Are there performance differences between using Fugue versus Koalas?
Yes, as we saw here, I mean, even though the benchmarks that we had earlier, those were not comparing across performance frameworks. There are differences. And because the implementation is very Pandas-like for the Spark Pandas interface, there are some issues it runs into which Fugue does not.
Okay, question from Aditya. How does Fugue perform in index operations? Does it perform better than the other frameworks?
At this point, I think this is kind of beyond my expertise. So rather than trying to answer something which I do not know about, I would like to defer this to Slack.
Oh, I can answer this because I'm involved in the project. Fugue does not have an index because Spark does not have an index. So the index is a questionable concept to bring to distributed systems. So Fugue explicitly does not have an index and thinks that the index only makes sense in the local setting. So within a partition, you can have an index, but the whole data frame is not globally indexed. Any more questions from the room? Okay, with that, let's give a round of applause.